Hello there, my name is Thomas. I'm representing investmentexcel.com in this session today, where we will show you how to apply the maximum likelihood technique to estimate parameters of a simple linear regression. We have three parameters to estimate: a constant, a slope parameter, and a standard deviation or a variance. Before we move on, let me just refer to other sessions I have made on more simple but relevant topics. For this topic on the maximum likelihood estimation particularly, it could be fruitful to look at a few sessions on the simple linear regression technique with ordinary least squares OLS. Alright, this video and the underlying Excel workbook are available at investmentexcel.com and spotify.com. I will now introduce first the data set, the time series for the estimation. We have 25 observations, and then we have an endogenous variable, which is the left-hand side variable in a regression framework, left-hand side of the equation of the equality term. It's the stock price. 25 observations obviously, and on the right hand side of the equality sign in the equation we have the GDP, which is then the explanatory variable that should ultimately be used to predict the price level. So we need to find a linear estimated relationship where the stock price is dependent on the GDP. And before I move into the estimation details of the maximum likelihood, let's just look at this model that we are actually trying to estimate. And remember, when we're talking about a model to estimate, we are talking about the true population model that we assume is the real world dynamics or relationship. So in this case, with a simple linear regression, the relationship is described like this, as I said on the left hand side. The stock price is equal to a parameter beta 0, the constant plus beta 1, which is equivalent to the slope in this relationship, times xt, which is the GDP, plus a normally but zero mean distributed random noise that is uncorrelated through time. Note the time subscript. So this is a model that defines or describes the true setting at every time period. So for each t, for each time over here, then this is the model. And moving from the true model, the true statistical framework, to the actual framework that we can estimate, we need to first use an expectations operator on both sides, because what we really actually want to estimate is the expected value of y. So I take expectations on both sides, and it's simply expectations to a constant here And here, please note that when we do regression modeling on all levels, we assume that the explanatory variables, they are constant. So they are non-random. So this is equivalent to taking the expectations to 2 constant, which yields a constant. So this is the process that we want, the true model that we want like to estimate. And we need to estimate beta 0, we need to estimate beta 1. These are the parameters in the linear relationship, but in order to do statistical tests, we also need to parameterize or estimate, the standard deviation or variance up here. With OLS, we know how to do it using the minimization technique of the sum of squared residuals with respect to the parameters, and then afterwards doing some manual calculation on sigma. With the maximum likelihood technique, we do something slightly different, although as I will show you later, we'll reach the same results. Equivalent to OLS, we start by building a model which is the estimated counterpart to the expression down here. So in this case, I just simply start by typing in some arbitrary numbers for the parameters. These can so far be seen as population parameters. We have not estimated the sample parameters yet. Right now I'm just building all model prices here, just on basis of the arbitrary inputs here. Then we take the residuals between the stock price and the model, and then here comes the tricky part, perhaps, that the way we try to minimize the difference between the stock price and the model price, which is obviously what we intend to do. We want to build the best possible model. We assume that the residuals are described by a normal distribution over here, and we put in the 0 from the distribution here and the standard deviation. And here in Excel you put in standard deviation and not variance. So this is why I refer here to the standard deviation. But normally when we build expressions like this, we use the variance. So it's not that easy. And the density that we would like to get is the highest possible density, because at the highest possible density we are at 0, at x equals to 0. That is where the residuals are equals to 0. So this is why I have typed in the residual here and the mean, describing the mean of the distribution, and then the standard deviation. And I do that for all of them. Now the PDF here can be interpreted like a probability or a likelihood. And now we don't just want to optimize the probability that the residuals go to 0 for this observation. We need to do it for all of them at the same time. So what we use is a joint distribution where it's assumed that that all observations are on correlated. So here, what we are actually trying to do now is to multiply all of these probabilities. It's just the same as if we wanted to calculate the probability of hitting 25 sixes in a row. It would be 1 6 here, 1 6 here, and so on, and we will get a joint result of the probability, a very, very low one. So here we multiply, but in order not to get a astronomous little value which Excel cannot handle, we can do something else. I mean, when you multiply all these, you will get to a number that Excel cannot handle. So what we can do is to use some logarithmic rules, mathematical rules. So we just take the log to each of these, and if we log a product string or product chain, we can just sum them. So here I have the sum, and now the idea is just to maximize this, because here we want to maximize probability. It's exactly the same after having taken the log, maximize. So I will do that now with respect to the three variables here. And there was a problem here because so here we get the result of the model, intercept, GDP, standard model, and the variance. And here I just changed a little bit, because if we want to have a unbiased estimate of the variance, we need to do some degrees of freedom adjustment, which I've done here. Over here you see the corresponding OLS estimates, which I have calculated just by using Excel's built-in functions, the intercept, slope, and here is a way of working out the standard deviation of the model by using this sum x my2. Not many people know this function, but it's actually very nice, and you will see we get the same results as in the ML. And then just note that all estimates here, they are unbiased predictors of the true variable, and with the degrees of freedom adjustment, also the standard deviation of the sample here is a unbiased predictor of the true standard deviation. So this was basically the maximum likelihood procedure, and obviously in the case with linear OLS, you can discuss if you should use one or another. Both are easy. When it comes to more complicated functional relationships, the maximum likelihood technique often has an advantage. Alright, I will leave you with this and say goodbye.